Sets and bags are two data structures that can be constructed using any of our collection implementations. Before we consider any implementation, let's consider their abstract definitions, beginning with the set. Like our generalized collections, a set is also an unordered collection. In addition, it must exclude duplicates. It models a mathematical set which has both of these characteristics. Any of our collection implementations could be used as the superclass for creating a set class. But because none of the implementations prohibited the addition of duplicates, we would have to override the add methods to enforce that prohibition. In the Java Collection Framework, there are three implementations for sets. None of them exclusively use an array or a linked list, because there are more efficient approaches. The tree set class uses a balanced binary search tree, specifically a red-black tree, topics we will encounter later. The hash set uses a hash table, another future topic. And the linked hash set uses a hash table in conjunction with a linked list. So the linked list is not the fundamental implementation, but one of its components. Now let's see how the abstract definition of a bag differs from a set. Although the Java Collection Framework contains the most widely used data structures, including several set implementations, it does not contain every data structure. A bag, which is sometimes also called a multiset, is an unordered collection that does allow duplicates. Although the C++ standard template library has such a data structure, the Java Collection Framework does not. Using a collection is one possible way to implement a bag. In fact, we could potentially use any of our three collection implementations. There are two additional methods that any bag class should have. The first is a method count that returns the number of occurrences of any element, returning 0, of course, if it contained none. Because a bag can contain more than one occurrence, the normal remove method would remove only one occurrence, so having a method remove all would provide the ability to easily remove all occurrences. Let's consider one application of the bag data structure, which will be a bag containing fractions. Our bag implementation is defined in the sorted linked bag class. It is a subclass of the sorted linked collection. The program will have a graphical user interface defined in the linked bag GUI class, which will contain an instance of the sorted linked bag class. Because the bag will contain fractions, the linked bag GUI class will use the fraction record. One portion of this program that has some noteworthy features is the fraction record. A Java record is suitable here because it spares us needing to write an explicit constructor. Because we are using a sorted linked bag, the elements of the bag must be an ordered type, so this record must implement the comparable interface, which means it needs a compare_to method. Comparing fractions is done by cross-multiplying them and returning the difference of the cross-multiplication. Overriding equals is important too, because fractions do not have to be identical to be equal. Because we are overriding a method from object, the parameter type must be object, unlike what we were able to do with compare_to. The syntax in this if statement is an addition to Java 14, referred to as an enhanced instance of, which spares the need for a typecast. If the parameter is not a fraction, false is returned. Otherwise, other fraction is an implicit typecast of other. The compare to method is called to check whether they are equal. This class also contains a toString method that converts a fraction to a string, and a static method that turns a string into a fraction, as well as one to reduce fractions to their lowest terms. So let's run this now and create some input values here. And we're going to begin this by adding to it several fractions. And we're going to do ones that are different from each other, but ones that are equal. So we know that 3/6 is equal to 1/2, so we're going to add that. So it says 1/2 was added. And then the next thing we're going to do is add 2/4. And again, it tells us that we added 1/2. One more time. This time we'll explicitly add 1/2. And so at this point, we should have 3 occurrences of it. So let's execute the count. And in fact, it tells us we have 3 copies of 1/2. The next thing, so that we can test them all, let's do a remove of 1, process that request, and it tells us that it was removed, and then do a count. And at this point, we should expect that there will be 2 of them, which in fact there are. And finally, the last one that we're going to test will be remove all. So when we do a remove all, what we should hopefully see that there should be none of them left. So when we do a count, we see that the bag contains 0 copies of 1/2. So we tested each of those various methods.